Hello, today we're pleased to welcome Tattwamasi, Amrutam from the University of Gurion. We'll talk on the existence or lack of non-commutative factors of a dynamical system.
Thank you. So thank you for the invitation. So I'll start with introducing the object that we are going to talk about. So throughout my talk, gamma is going to be a discrete group. And A is going to be a unital bigger. So when I say that A is a gamma cyst algebra, what I mean is that there is a homomorphism from my group gamma to the star automorphism solution. And I have a faithful representation of A inside some Hilbert space V of H. So using this, what we can do is we can define a new representation, sigma, of A inside V of L to gamma H, where L to gamma H is the collection of all H valued square soluble functions. And this is defined by sigma of a xi t at any point t is just xi of phi t inverse A. And xi is an L to gamma H. A is an A. And T is in my group gamma. And we also have a left regular representation of my group gamma in V of L to gamma H. This is basically the translation of the elements. So this is lambda S at xi at any point T is xi of S inverse T, where xi is an L to gamma H and ST, these are in my group gamma. So now what we do is that the reduced cross product is defined to be the span closure of sigma A lambda S as A varies over A and S is in my group gamma. And then we close it in the norm in V of L to gamma H. And the reduced, so this is called the reduced cross product.
You're feeling psi and something that is high of T inverse
A, yeah.
high C of T.
Yes.
Okay, there's something exactly like C.
Yeah, thanks. And this is the reduced cross product. And we get the group cyst algebra, which is the span closure of the lambda SS, just without taking the sigmas. And by construction, it follows that my group cyst algebra is contained inside the cross product. And this inclusion is a C-star subalgebraic inclusion. Okay, so moreover, we have a canonical conditional expectation from the cross product to A, which is basically taking sigma A lambda S. The sigma A faces identity and zero otherwise. So conditional expectation is nothing but a projection onto the space. And this map is well behaved with respect to the group action on the cross product. And in addition, maybe I write here, if there is a gamma invariant state P on A, then we can define another gamma equivariant conditional expectation from the reduced cross product to the group stitched algebra, which is basically taking A lambda S to phi A lambda S, and then just extending it canonically. Okay, good. So the problem that we are interested in today is to find conditions on either the group or the action. Okay, so here maybe I just should a remark. If I have an inclusion of gamma stitched algebras B inside A, then we naturally get an inclusion of B cross product gamma inside A cross gamma. Just by such that every intermediate stitched algebra C is again a cross product. And whenever such a, so basically we, if such a thing happens that every intermediate of this form is a cross product, we say that we think of this as a non-commutative factor. So this is where the name comes from.
Cross product by gamma.
By gamma, exactly. So what I so C is of the form A1 cross gamma, where A1 is a subalgebra of A containing B. So now maybe a bit of known results, what we know.
So is this actually true then for factors in the conventional sense of the system?
Yes. So if I have something like this, and I know that A is some C of G cross gamma, then it follows that G must be a factor of X, and I have a factor to Y.
Okay, but if you actually know ahead of time that A is such a thing,
Yeah.
rather than it automatically cross.
No, we do not know. I mean, if A is such a thing, then this happens. So, but in generally, A may not be such a thing.
Yes.
Yeah, we're going to see that in further ahead. Was that your question, or?
Well, you were saying that you think of when this actually happens, that E is a non-commutative factor of A. So I was
No, C is a non-commutative factor of.
C is a non-commutative factor. Oh, okay, all right.
Okay, so this is a theorem of Suzuki. From 2018, yes, that 2017 actually, that if gamma is a group with property AP, and I have a factor map from X to Y with the assumption that gamma acting on Y is free, then every intermediate C-star algebra C which contains Cy cross gamma and is contained inside Cx cross gamma is of the form C of G cross gamma for some factor. And a similar result holds in the von Neumann algebra setup as well. So you just replace the freeness of the action by essential freeness. Yeah, so property AP right here. So property AP just means that we have a net PI of finitely supported complex valued functions on my group gamma such that the corresponding multiplier function so if I look at this map, then this thing converges to identity in the pointwise norm topology. And MPI is just the multipliers from here to here, which just sends lambda is to so B is any other unital C-star algebra.
So, walls is also walls.
Yes. So actually, even if we do not assume property AP, without the property AP assumption, so what we can show here is that the conditional expectation keeps C invariant. This is and then property AP would actually imply, this is where AP comes in the picture, that C is exactly the cross product by E of C. This is actually a result of Suzuki. Okay, so now the question is what happens. So in the result of Suzuki, we cannot take Y to be a single point because his assumption is that the action on Y is free. So what we could show though is that that if gamma is an cylindrically hyperbolic group, and the amenable radical of the group is trivial, and I have an action on a unital C-star algebra which is not faithful, then every intermediate C-star algebra B is a cross product again. should have said here with property. So just so an example of an asymptotically hyperbolic group, basically hyperbolic groups, then outer automorphisms of my free group, some non-examples in a finite group, given SLN G for n bigger than equal to 3, so they are not asymptotically hyperbolic. Even virtual input. Yeah.
And such a thing.
I don't know. Well, yes. I mean, the theorem, yeah, no. In the so actually, this assumption here forces gamma to be theta simple. So, which is equivalent to saying that the group theta algebra is simple. So now, but the thing that so this theorem is again in a very different direction to that of Suzuki's, because in Suzuki's theorem the action is free. Here I have a non-faithful action on A, and also the assumption here on the group forces my group to be a theta simple group. So the question that we wanted to ask are there faithful actions for who is the intermediate algebra? Is a cross product. And so this is what we wanted to prove in the beginning, to find such an example. So maybe I introduce a definition here. So XD is a metrizable gamma space. So the action gamma on XD is called equicontinuous. If for every epsilon bigger than 0, we can find a delta depending on epsilon, such that whenever the distance is less than delta, then the distance between Sx and Sy must be less than epsilon for every group element S in gamma. Maybe I introduce another definition here. convergence action. So again, gamma is acting on a metrizable space GD. This is called a convergence action. If for any sequence gamma n of my group elements, and this must be distinct, we can find a subsequence gamma in K and points A, B in G such that gamma in K, when I restrict it to G minus A, it converges to B on compact sets. So on a G minus A. So A and B are distinct points on G. An examples of such an action is basically the free group F2 acting on the Gromov boundary.
What's the same symbol between the gamma and A and the AB? This answer.
Yeah, and
Thank you.
okay, so using this convergence action, and we say that gamma is a convergent group if it admits such an action. So gamma is a torsion-free convergent group, and gamma is acting on space XD, and this is an equicontinuous action. Then every intermediate C-star algebra B is a cross product. And this Y is realized by a pattern. Moreover, what we can also show here that if gamma is SLN G in bigger than equal to 3, sorry, in bigger than equal to 2 is also good, then and gamma is acting on XB, this is an equicontinuous action. Then for every intermediate algebra B, you get that B is invariant under the conditional expectation. And since, I mean, okay, so if any exactly true, then B is a cross product.
For this example, it's going to be the same three actions. Such as,
Equicontinuous pre-reactions,
yes, and
yeah, yeah, being automated actions. Those are basically the pro-finite completion of that would do. Okay, so now in these theorems, this condition forces my group gamma to be a C star simple group. And now the natural question comes as to what happens. And gamma is a not C star simple group. And in this case, we see that the results are very different to the ones that we have. So I start with the following proposition. So gamma is not C star simple. And A is a gamma C star algebra. So if I look at AI and I pick an ideal I in my group C star algebra, which is two-sided, closed, and non-trivial. If I look at AI, which is the span of eta tilde, these are in I, and A is in A, then the first thing that we can show is that AI closure plus the group C star algebra is an intermediate C star algebra. And if I further assume that if there is a gamma invariant faithful state on A, then B intersection A is C. So if we show that now the only obstruction is that if we can show that E of B is not C, then B cannot be a cross product in a canonical way. So maybe I give an example. say gamma is just the simplest group element, G mod 2G, which is we denote by ES, and this is acting on a space X, and I assume that X has more than 2 elements. And what I do is I consider the augmentation ideal, which is AE so this is known as the augmentation ideal. And then it's well known that G is an ideal in my group CR star gamma. And I can do the same construction here. So I look at B, which is AJ closure plus CR star gamma. So now what I do is that since my there are more than 2 points in my X, so what I can do is I can choose X1, X2 in X such that X1 does not belong to gamma X2. So I can choose X1 such that it is away from the orbit of the point X2. So find open sets U V such that here this is X1, gamma X2 is here, such that U intersection V is an empty set. This is just Gurison's lemma. Oh, this is just the separation of points, and then find F in C of X with F between 0 to 1. F of X1 is 1, and support of F is contained in E. This I can do by Gurison's lemma. So now what I do is I look at A tilde, which is lambda E minus lambda S, F, and then lambda E minus lambda S. So then A tilde is just F minus S dot F plus S dot F, then minus S dot F lambda S, and then minus F lambda S. It's just calculating it. And it turns out that E of A tilde is F plus S dot F, because it just kills every group element other than the node identity. No, I just interchange them. Okay, and then what I want to show is that E of A tilde at the point X1 is basically F of X1 plus F of Sx1, which is bigger than or equal to 1. And E of A tilde at the point X2 is F of X2 plus F of Sx2, which is 0, because support of F was contained in U, and U intersection V is an empty set. So this basically shows that we could find an element A tilde in B, which is shows that E of A tilde is not constant. So therefore, B is not the reduced C-star algebra, and hence B is not a cross product. This is of course in a canonical way. Now, this phenomenon is not limited to G mod 2G. There is nothing particular about it. So what you can show actually is that so this is for gamma is an ICC group, and I pick an ideal I in CR star gamma. I is not trivial. Then B, which is AI closure plus CR star gamma, is not a cross product. In a canonical way. So basically, it just says that if we want to find examples of inclusion such that every intermediate is a cross product, we need to necessarily restrict ourselves to C-star simple groups for such cases. Now, the theorem becomes a bit more complicated for non-ICC groups. So if gamma is a non-ICC group, then what we can do is we can look at gamma F, which is the collection of all finite collection of elements with finite conjugacy class. And then the theorem says that so gamma is a non-ICC group, and I assume that the number of elements in my conjugacy class is more than 2. Then if I look at, then there exists an ideal I in CR star gamma such that B is not a cross product. Of course, here B is basically is always AI closure plus the group C-star algebra prime group. Now we do not know if we could remove this assumption of gamma if bigger than 2 in general, but we can state the theorem much generally when I'm looking at compact Hausdorff spaces. So if A is C of x and my number of elements are bigger than 2, and then we can pretty much say, and here gamma is a not C* simple group. Then there exists an ideal I such that B, which is not a cross product.
What's wrong with just 2 elements? I mean, usually you want to have a strictly bigger than strictly more than 1 element, but strictly more than 2 elements, I haven't seen that condition.
So the problem is exactly when G mod 2Z is acting on, say, 2 points. So then in this case, if I look at, so this is my x. If I look at C of x cross G mod 2Z, then this is isomorphic to M2C.
Yeah.
And
Sure, yeah.
and then we can show that there are actually no intermediate algebras between CR star G mod 2Z and the cross product.
You're saying you have an irregular intermediate subout.
I'm saying there are no intermediate subalgebras.
No, none at all.
Yeah. Between CR star G mod 2Z and this cross product.
Well, this says there exists one. Okay, not a cross product.
Yeah. So the point here is that we can find an intermediate one which is not a cross product.
Yeah, but you could just. All right, yeah, you could say whenever there is one, there's one. There's also one that's not a cross product. Then.
Yeah, sure. We can say that, but the thing is that so I'm just saying that if it is 2, then there are. I mean, we don't have any intermediate one, so that's why we just need it.
If you take 3 points, then there is.
Yeah.
But it's a cross product.
It's a sorry. If I take 3.
If it's 3 points, then that's included in the first question. There is one.
Yeah, I'm just saying there is one which is not a cross product.
Oh. Okay. Is there also one which is a cross product?
Yeah. Just take the factor map to 1 to 2 points, and then there is one.
All 3, I think, 3 points.
Yeah.
It will be a cross product factor between. I mean, so one diagonal, one of them three-vector matrices. We have intermediate algebra, but none of them are products.
None of them are cross product.
I don't see how the only ones we have are block diagonals. So,
Yeah, right. Well.
Right. Yeah.
Thank you.
Okay, so exactly. So the point here exactly happens when we do not know how to handle when G mod 2Z is acting on A in general. Then we do not know how to handle that case. If we could do that, then we can positively remove this assumption here. Okay, so finally, we 5 minutes. So, so in this case, we want to consider an equation, say G, and this is acting on the circle by irrational rotation. Now we know that there are intermediate algebras B, which are not cross products. But still, the question is, can we still give some sort of description of these intermediate algebras? So what we do is, so the answer is yes. So to such an object B, what I can do is I can associate a collection of ideals, which are basically all those elements A in CR star G, such that e to the power INX A is again an element in B. And it turns out that this is an ideal in CR star G. And what we can show is that if I pick an arbitrary element B in B, then B can be approximated by elements from here. So a finite sum of the form e to the power INX AN, where ANs are in IBN.
What is
X. So these are the continuous functions here.
Oh, okay. Oh, I see.
So there, I mean, of course, we can still go on to say things about the simplicity of these ones, depending on these ideal functions and so on, but maybe that could be for another day. So I stop here.